And the last topic that I want to talk about in this section is local and global extrema. It says a local maximum or local minimum at x equals a. They're sometimes called a relative maximum or minimum, respectively, is the output at the highest or lowest point on the graph in an open interval around x equals a. So, and basically it's saying if the function has a maximum at a, then every y value around that point is lower than the output at a. Okay, and same thing if it's a minimum at x equals a, then every output value or every y value around that point is lower than the output at a. It's common sense. It's a formal definition of extremis, and so the functions will have global maximums and global minimums as opposed to local minimums and maximums. Okay, so these are peaks and valleys in like locally, and these are globally, meaning for the entire function. So if it's a global maximum, that's the highest point in the entire function, and if it's a global minimum, then it's the lowest point in the entire function. Now, some functions will have global minimums and maximums, and some won't, same as with actually local minimums and maximums. So for example, if you look at the function that we're familiar with, the quadratic function, it has a local minimum, which is also a global minimum at the vertex if it opens up. But then what about the maximum? It doesn't have either the global maximum or a local maximum because it continues to grow indefinitely, right? So if you have a function like that looks like this, it may not have a local minimum or maximum. Like this function, for example, or global minimum and maximum for that matter. So here it looks like the function flattens out a little bit, but then it continues grow after that. It's not counted as a local maximum unless it was going up and then it started going down after it reaches this point. So basically, your turning points are your maximums and minimums, as we discussed earlier. So here's an example of a function, and this function, it has two local maximums, right? One at x equals 2, the maximum is 2, and another one at x equals 5, and the maximum is 5. And it also has a local minimum at like 3 plus something, and the minimum is about negative 1.75. So it has 3 local extrema. But what about global? Well, global maximum is the highest point in the entire function. So it will be this this maximum of 5 at x equals 5. Now, what about global minimum? Well, there's only one minimum, but there are function values that go lower than that local minimum. So this function does not have any global minimums. And here's how you would write it down. You could say this function has local extrema. It has a minimum at x equals 3.3, and the function value there is 1.75. and it has maxima. The plural for maximum is maxima at x equals 2, and the function value there is 2, and also at x equals 5, and the function value there is 5. Now, your global extrema also count as local extrema. They're both local and global. Now, let's list the global ones. Okay, for global minimum and maximum, there could be only one each. So we will use these words in singular form here. So global maximum happens at x equals 5, and this is what it equals to, the y value, and there is no global minimum. So again, both of them are, both the maximum and minimum are extrema. Now, why is it important? Why are we talking about it right now? Well, in a lot of application problems, you will be looking to maximize your function. Let's say if it's maximizing the profit function, or maximizing the volume, or maximizing the area. In all of these applications, we're looking for a global maximum. So that's why these are very relevant. So let's take a look at the next problem. So here we have an open top box is to be constructed by cutting out squares from each corner of a 14 centimeter by 20 centimeter sheet of plastic, and then folding up the sides. Find the size of squares that should be cut out to maximize the volume. Okay, so here's our dimension. We have 20, this side is 20 centimeters, and this size is 14 centimeters. The squares are actually labeled for us. They're W's. Okay, so the box. Remember, they're asking us to maximize the volume of the box. So how do we calculate the volume? The volume is basically your length times width times height. That's the volume. The formula for the volume of the box. So we have to figure out the length, the width, or vice versa, and this would be our height of the box. Okay, so since we this whole side is 20 centimeters, how long is this side? Well, since we cut the W's out, we have 20 minus 2W left. Okay, for the length. For the width, right here, I'm gonna write it. For the width, again, the full width was 14. We cut out W and W, so it's gonna be 14 minus 2W. Okay, so our volume here is the length 20 minus W, 2W, multiplied by the width 14 minus 2W. All right, and then we need the height of the box. So when we fold it, when we fold the sides, the height will be W. So it's another W right here. All right, so how do we figure out the volume? Here it says use technology to estimate the reasonable maximum, because we don't have the tools right now to actually find the W which will give us the maximum value. That you're going to learn those tools in calculus. When you take the calculus class, you will be able to spot that that maximum without graphing, just by working with the equation. But for now, for us, we're gonna use technology. So here's the graph of my function. I typed in the equation that we got. And instead of W, I have X, and instead of volume, I have Y. But Y actually represents the volume created, and the volume depends on your X value, or the W. Okay, so what do we see? We see that the function is increasing from 0 to about here. And then it's actually starts decreasing when it hits the minimum here, and then it goes up again. Now, when you're looking at the functions and so you're solving applied problems, you have to actually think of what makes sense. I mean, do we really get a negative volume here? Because we're talking about y represents volume, right? And here we have negative values. Why is it happening? Well, if you look at our box, and the width of it is 14 centimeters. Now, how big of the squares can we cut out? Well, the side of the value of the W cannot be bigger than the half of that width of the plastic that we have, plastic piece that we have. So the maximum value for W is actually 7, right? So everything that we see beyond 7 is irrelevant in our context. So we could actually zoom in to just look at this piece of the function right here between 0 and 7, because that's what's relevant. Okay, so it looks like we have a maximum right here at 2.7. So the W of 2.7 will give us the maximum height. So we're gonna write here our conclusion that the squares with the sides of length 2.7 centimeters will yield the maximum volume of our box. That's how we use the maximums and minimums of the functions. And sometimes you have to find the maximum, like maximize the profit, maximize the volume. Sometimes you have to find the minimum, like minimizing the cost. Those are all examples of when you'll need that information. All right, so I want you to try this problem. I don't know why that picture is there. So I have used technology to find the maximum and minimum values in the interval between -1 and 4 of the function f of x equals -0.2 and then multiply by x minus 2 quantity cubed, multiply by x plus 1 quantity squared, multiply by x minus 4. All right, pause here if you have to. And let me know if you run into any problems. I'll see you in the next video.